Good afternoon. Good afternoon. Hope all is well. Everybody's doing all right.
Good afternoon.
How's it going? How's it going? So, sorry about last week. Um, it ran late. By the time I got home, it was super late. So, yep, I missed that window, but I guess I had to get the shot. So, at least that's taken care of. Don't have to worry about it anymore. So let's see. Where did we leave off? Where did we leave off? I believe it was chapter 4. Guess you guys can help me out. Did we get started in chapter 4? Anybody know? Remember from the notes?
Looks like 4.1 scatter diagrams and correlation was the last chapter.
That's all we did. That's what I thought. Okay, cool. I just want to make sure. Okay, so we'll do 4.2 and 4.3 today, and go from there. Thank you for that. I appreciate it. Okay, so looking at 4.2 least squares regression. So the least squares regression line is going to be the line that minimizes the sum of the squared errors or residuals. So we're going to come back to that shortly. We talk about errors and residuals; those are same terms. So another way of explaining that, so the line that best explains the relationship of the data. So in other words, it best sums up the pattern of your data. So this is an example of that. Just the line that best sums up those points. Scrolling up. So there are two ways that we will be given information to be able to find a regression line. Anybody still using that last sentence right there? Okay. One of the ways is if they give us certain pieces, like they can give us all of the data values, or they can give you pieces from the data. In other words, the correlation coefficient, standard deviation of the Y values and X values. You'll see in a second what I mean by that. But it can give you information for your regression line two different ways. So this is our regression line right here. And that's Y hat equal to B1 X plus B naught or B0. So that Y hat, that part of a triangle with no base over your variable is called a hat. So if you had X, would that be X hat or a hat? But that's Y hat. And that's going to represent our predicted Y value. So we'll get more into that in a second. The way we would be able to calculate B1 is by taking our correlation coefficient and multiply it by the standard deviation of our Y values or the standard deviation of our X values. The breakdown, hold on. So get all of this in there. There we go. And then B0 is Y bar minus B1 times X bar. So Y bar is the mean of your Y values. X bar is the mean of your X values. So you see in the green right here, your X values are your explanatory variables. Y values are your response variables. We talked about those last class. All right. Can we scroll up? So should have put regression line or regression equation. I'll leave it like that. But regression is used to predict an outcome based on previous observations. All right, I scroll up. All right, so we're going to go ahead and find a regression line with them giving us those pieces of information. So notice they give us the regression line, they give us the mean of X, standard deviation of X, the mean of Y, and the standard deviation of Y. All right. So they give you these 5 pieces to your information. First thing we do is find B1. So if you go back to your formula, we have to find B1 because B1 is a part of the calculation of B0. So we have to find B1 first. So you plug in the values accordingly. So R correlation coefficient is -0.946. And then we have our standard deviation of Y over our standard deviation of X. So 5.612486 over 2.44949. So that in the calculator, that gives you -2.1676. Then we'll find B0, Y bar minus B1 times X bar. So 10 minus -2.1676 times 4. So make sure you don't lose a negative when you do your substitution. That gives us 18.6704. All right, any problems? So now that we have B1 and B0, we can go ahead and plug it into the formula, to the equation. And that's it. And so in MATLAB, it will be set up this way, in which they will have boxes, for you to plug in the numbers. And make sure you plug in the appropriate, box beside X. B1 goes beside X, B0 does not. So make sure you're careful with that. Also here, that's the same thing as this one. So notice 18.6704 is positive, 2.1676x is negative. So as long as that's the same, it doesn't matter which order you put it in. As long as the 2.1 is negative and the 18.6 is positive, it's still the same result or the same equation. So. All right, questions on that? Can I scroll up? So the next one tells us to find a regression line. Predict the distance the ball will travel when hit with a club head speed of 103 miles per hour. Am I done with the purple? And then determine the residual for the predicted value from the result in B. Is the distance in the table above or below the average among balls hit at 103 miles per hour? So we'll do all of that. Let me write some of this better. All right, can we scroll up? So these are the same values from 4.1. So this time, instead of giving us R, X bar, Y bar, S sub X, S sub Y, they give us the data values, the observations. So we're going to plug those into an app website or calculator of some nature. Remember I told you that's what we should be using. Now, if you want to do it by hand, you can, but you saw the pieces that you had to calculate first, those 5 pieces first, and then put them into the formula. So yeah, so if you just get the data value straight, I would go to easycalculation.com and go from there. So give you guys a chance to figure it out. All right, can I go to the website? All right, so I'll just go to the website and we'll come back to the notes. So once again, what I would do is type in what I'm looking for, regression line, and then easy calculation. So I always type what I'm looking for, and then type in easy calculation. And the first one normally is it. Very similar to correlation coefficient, where we have our X and Y values. So, all right, almost there. All right, so there we go. They give us the slope. The slope is always what's in front of X. Y-intercept is the other number, just in case Math Lab asks you. The slope is always what's in front of X. Y-intercept, I think I wrote that in the notes as well. And then here's the regression line altogether, 3.166 in front of the X, negative 55.797. Questions on that before we shoot back to the notes? All right.
In terms of like showing work for like the test or something, would you expect it like because like I set up an Excel thing kind of like what that was too.
Mm-hmm.
I mean, are you expecting to see work for this or okay?
No. With you guys and some of the stuff, you may not have much work because you're using an app or something like that or Excel, and that's fine. Yep.
All right, cool. Thank you.
Yep, not a problem. So that's how we would do A. That's how you would find a regression line. So really, it's a lot of application when it comes to this class, not necessarily, calculation. Yep. All right, so everybody okay with A? So now B, it says predict the distance the ball will travel when hit with a club head speed of 103 miles per hour. So that means for B, they're telling you X is 103 and they want you to plug that into your regression line calculator. Your regression line equation, not calculator, but regression line equation. All right, so plugging it in, type 3.166 times 103 minus 55.797, and that's 270.3 yards. So that's the prediction that the ball, not the ball, well, I guess you could have said the ball, but that's the prediction that this equation is giving, that the ball would travel based on past information. And that chart is our past information, our past observations. Right. Questions on what B asked? All right. So C, determine the residual for the predicted value from the result in B is the distance in the table above or below average balls hit at 103 miles per hour. So the way we calculate residual or error, when we talked about that when we first got into the section, you take your observed Y and minus your predicted Y. So in other words, that just in symbols, that's Y minus Y hat. And so you have to get that Y from the chart. And 103, when he hit the ball at 103 miles per hour, it went 274 yards. So you see right here, 274 minus that 270.3. Notice the first value, we got that from the chart. Y hat is what we got from the equation. And you would subtract them. Got 3.7 yards. And so our conclusion, the observation in the chart is above the average balls hit at 103 miles per hour. And you see what I wrote there in the purple, it is above because it is positive. So if that was negative 3.7, then it would be considered below average balls hit at 103 miles per hour. All right. Any questions? Any questions? Make sure we're okay. All right. So that's 4.2. Are we okay to scroll up to 4.3? All right. So 4.3, the coefficient of determination. It measures the proportion of the total variation in the response variable that is explained by the regression line. So it basically tells us how reliable the regression line is. And to calculate it is the correlation coefficient squared. Talking about our R, that's R squared. All right. It is denoted by capital R squared. It is between 0 and 1 inclusive. R squared equal to 0 means the regression line has no explanatory value. R squared equal to 1 means the regression line explains 100% of the variation in the response variable. All right. So here, determine and interpret the coefficient of determination for the club head speed versus the distance. If I don't black. All right, so the first thing we'll do is find a correlation coefficient. Now we already found that for this set of information. Once again, we're just talking about the club head speed versus the distance. Got 0.939. Once you find the correlation coefficient, you're going to square it. Here we got 0.882, or in other words, 88.2%. So what this means for us is that 88.2% of the variation in distance is explained by the regression line. 11.8%, which is 88.2 minus 100. The variation is explained by other factors. So in other words, whether it be the wind, maybe he turned or twisted his hips one way when he swung the golf club that he normally doesn't do, or something like that. So something else explains why 11.8% other times it doesn't fall into the same pattern as the other ones. So that means this regression line has an 88.2% reliability. All right. Any questions? All right. Everybody good? All right. I'll move to the next page. All right. So let's start chapter 5. I know I at least want to do 5.1 today. Didn't meet with you guys at all last week. But that's it for chapter 4. It's only those 3 sections. So that means we're done with lecture for test 2, because test 2 is 3 and 4. So, make sure you guys are stay on top of this stuff. Don't forget it's only an 8-week course. So, make sure we stay on top of our assignments. All right. So 5.1, probability rules. Probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. All right. Next thing, the law of large numbers. As the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So in other words, the more and more you run a trial, the greater the chance you actually get into the true probability of something occurring. All right. All right, so an experiment is any process with uncertain results that can be repeated. Example of that is flipping a coin. Your sample space is the collection of all possible outcomes of an experiment. So when it comes to flipping a coin, the sample space would be heads and tails. Also, the sample space is normally denoted by S. Mhm. And then your event is going to be any collection of outcomes from the sample space. An example of that's tails. So if you want to know the probability of landing tails, tails will be your event. And that's normally denoted by a capital letter, any capital letter. We try not to use S though, because S is your sample space. Any other letter is good to go though. All right. So we got two rules of probability. They start off with just two. I should say that, not just two. So the first one, probability of your event E, probability of E. Your probability will always be in between 0 and 1, inclusive. By holding on to the event. And then the sum of the probabilities in all outcomes is going to be equal to 1. So if you're talking about your sample space, if you add up all the individual probabilities of each event in your sample space, they will add up to 1. So notice how we had heads and tails. If you look at the probability of heads added to the probability of tails, they will add up to give you 1. So that's what that means. All right. So the probability model just states that it must satisfy rules 1 and 2. So they ask us to verify that this is a probability model. I believe these were colored M&Ms. And they were looking at, oh, still have my eraser on. Looking at what we have here, our colors of the M&Ms and the probability that when you dig your hand in the bag, you will get that color of M&M. So we have brown 0.13, yellow 0.14, red 0.13, blue 0.24, orange 0.20, green 0.16. All right. So you have to ask yourself, does it fit each rule? And rule 1 is satisfied because each probability is between 0 and 1. Then rule 2 is also satisfied because when you add up each one of those probabilities, they give you 1. And so since the model satisfies rules 1 and 2, it is a probability model. All right. So another few facts or properties. An event is impossible if the probability is 0, in other words, 0%. An event is a certainty if the probability is 1, that would be 100%. The closer a probability is to 1, the more likely the event will occur. The closer the probability is to 0, the less likely the event will occur. An unusual event is an event that has a low probability of occurring. So this typically will be an event with a probability less than 0.05 or 5%. All right. So that 5% is not set in stone, but that will be our standard that we use, for this book. 5%. Less than 5%, it is considered unusual. Hold up. All right, so gonna calculate some probabilities. Got two different approaches. First one is the empirical approach. We take the frequency or the number of times that that event occurs over the number of trials of the experiment. I wrote the experiment right there. All right. So first example, dealing with this, an insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim. Based on these results, what is the probability that a teenager will file a claim in a given year? All right, so all we would do is take the 24, place it over 182. And there we have approximately 0.132. Any problems so far? So when you get this value, MyMathLab may give you sentences to choose from versus just putting in 0.132. Sometimes that's all they ask of you. Put in 0.132 and that's the answer. Sometimes they'll give you a sentence to choose from in order to state the conclusion. So if it says something like this, notice what I have here. It says, so for every 100 teenage drivers, we expect about 13 to have to file a claim. So if they got 100 right there, that means they took 100 and multiplied it times that 0.132. Okay. Over here in the blue box, I got right here, if they had, so for every 1,000, then you would take 1,000 and multiply it times that 0.132. So then they should say something, we expect about 132 to file a claim. You know what I mean? So that's how you would do that. Whatever this number is right here, you take that, multiply it times that probability, that decimal value for your probability, see what number you get, and it should match up right here. And that's how you would determine if you have the correct sentence or not. You know. All right. Questions on that? Make sure we're okay. All right. Let me scroll up. All right, so next we have the classical method. So we take the number of outcomes in E, place it over the number of outcomes in the sample space. And it should say event E, but talking about your event. All right. So N of E, in parentheses E, represent the number of outcomes in E. N of S represents the number of outcomes in your sample space. So a mini example of that. Flipping the coin and landing tails. All right, so first thing you want to do is examine your sample space. And so in our sample space, heads and tails are our only two options. So the number of outcomes in our sample space is 2. Then we want to know the outcomes, or we want to know the probability of landing tails. Tails is only considered one outcome. So the number of outcomes in that event is 1. So you place that 1 over 2, and that's your probability. So you place the number of outcomes in your event over the number of outcomes in your sample space. Any problems with that? All right. A single die is rolled. What is the probability of landing a number greater than 2? So just like before, you want to examine all of your outcomes in your sample space. So if you know a single die, if you're not, for a board game Monopoly, talking about it has 6 options total. 1, 2, 3, 4, 5, 6. The pips. 1 pip, 2 pip, 3 pips, and so on, all the way up to 6. So we have 6 possible outcomes. So make sure you're careful here. This 6 and this 6 have nothing to do with each other. And what I mean by that is that this could have been 1, 2, 3, 4, 5 triangle. The question is, how many outcomes do you have? You have 6 outcomes still here. It's just that one of them is a triangle, so your number would be 6. Okay, so I don't want us to be confused and make it seem like because this is a 6, then that has to be a 6. No, it's a count. You're supposed to count how many outcomes you have in your sample space, how many total outcomes you have. That's the numbers that 6 should be. Right here. Put that back. All right, and then we're looking at numbers greater than 2 in that sample space, 3, 4, 5, 6. And so the number of events, number of outcomes that fit that description would be 4. 3, 4, 5, 6. Once you have those two numbers, place the 4 over 6. We can reduce that by 2, and that leaves us with 2/3. Don't have to convert it to a decimal unless MATLAB asks for it. Any problems before we go to the next one? All right, so here we have a pair of dice is rolled. Compute the probability of rolling is 7. Then compute the probability of rolling snake eyes. And that would be a 2. All right. So the first thing we want to do is establish our sample space, the number of our sample space first. So of course, we don't want to have to write out all of our possible outcomes when you're looking at a die, a single die that has 6 options. We have 2 of them. So, because you would be looking at when it's 1 and 1, then when it's 1 and 2, then when it's 1 and 3, all the way down to 6, then when it's 2, 1, 2, 2, 2, 3, 2, 4, all the way down to 6, and so on. So the best way to do this, to calculate this, is this right here. When you have a die and there's 6 options on that die, then you have a second die, 6 options on that die. You multiply your options together, and that'll tell you how many possible outcomes that will occur. So that's the fundamental counting principle. So we just do 6 times 6, which will give us 36. If you had a die that has 6 options, but then another die had 8 options, you do 6 times 8, that'll be 48 possible outcomes. So that's all we're doing right there, is just multiplying the total number of outcomes from each die, and that'll give us a total number of possible outcomes from both of them. Okay, so our sample space, the number of our sample space will be 36. Now our event, we're talking about rolling a 7. We're looking at all possible ways of rolling a 7. So die 1 being 1, die 2 being 6, and 2 and 5, 3 and 4. Now die 1 being 4 and die 1 being 3, die 2 being 3 is different from 3 and 4. So then you explore the other ones. So notice we have 6 possible outcomes, 6 possible ways that you can get a 7 rolling 2 dice. So once you have your two numbers, the number of your event and the number of your sample space, place your event over your sample space 6 over 36, and that reduces to 1 over 6. All right, any problems, any problems? All right, B, rolling snake eyes. That means rolling the 2, 1 and 1. We've already established our sample space. It's 36. And there's only one way you can get snake eyes. That's when die 1 is 1 and die 2 is 1. So you just do 1 over 36. All right, any problems, any questions? All right, scrolling up. All right, so this next one, suppose a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. So first, we're looking at A, estimate the probability of having 2 boys and 1 girl using the empirical method, compute the probability of 2 boys and 1 girl using the classical method. So give you a chance to write that down. All right, so let's look at A first. Want to compute or estimate the probability of having 2 boys and 1 girl using the empirical method. So I just did 2B, 1G, 2 boys, 1 girl. The probability of getting 2 boys, 1 girl. All you do is take the 180, place it over 500, and that's 0.36. That's the empirical method. Ooh. All right, so now for B, compute the probability of 2 boys and 1 girl using the classical method. First thing we'll do is actually create a tree. Oops, I'm going up too far. Create a tree that would actually map out all of the possible ways of getting 2 boys and 1 girl. Well, not necessarily 2 boys and 1 girl, all of the possible ways of getting or having boys and girls, you know, with just 3 kids, with 3 shots. So we start off with firstborn being a boy. And then from there, you have 2 options, a boy and a girl for the secondborn. And then from there, you have 4 different possible scenarios that could occur. So from boy, boy, you can do boy, 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 girl. And then from boy, girl, you can go boy, girl, boy, boy, girl, girl. And then you can do the same thing if you have a girl first. So if you have a girl first, from there are 2 options, girl, boy, girl, girl. And then from there, the 4 options, girl, boy, boy, girl, boy, girl, 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 boy, then girl, girl, girl. So those are 8 possible scenarios that could occur if you were to have 3 children. All right. Now then our event is having 2 boys and 1 girl. Doesn't matter the order, but having 2 boys and 1 girl. And I've put the asterisks where we have that scenario. So you can have boy, boy, girl, boy, girl, boy, girl, boy, boy. So those are your 3 possible scenarios of having 2 boys and 1 girl. And then once you find those 2 numbers, place your event over your sample space, and that will be your probability. So that's 0.375. All right, any problems? Well, that's it for 5-1. Any questions on anything so far? Any problems? Let's look at 5-2, see if I want to do 5-2 today. Yeah, let's do 5-2. I think I want to do 5-3 and 5-4 together. Yeah, let's do it like that. And don't want to do 5-2, 5-3, and 5-4 together. Okay. So we'll do 5-2 and then call it a day as far as lecture is concerned. So the additional rule and complements. So 2 events are disjoint if they have no outcomes in common. So they're all disjoint outcomes, also called mutually exclusive events. All right. So if your two events are disjoint or mutually exclusive, remember disjoint and mutually exclusive are the same thing, and you want to find the probability of either one of those events occurring, you would just add the probabilities together. So if they don't have anything in common, you can just add them together, and that will be the probability of either one of those occurring. All right. So before we actually do an example of, or example using that, let's look at our deck of cards and how we will establish what cards are what. So standard 52 card deck means no jokers. So there are 4 suits: spades, clubs, diamonds, and hearts. 2 black suits, there will be spades and clubs. 2 red suits, diamonds and hearts. 13 cards each suit. There will be 3 face cards, 12 regular cards. Your face cards: king, queen, jack. Regular cards: ace, 2 through 10. So your ace is not a face card. Ace is not a face. All right. Scrolling up. All right. So suppose a single card is selected from a standard 52 card deck. Compute the probability of drawing a king. Compute the probability of drawing a king, queen, or jack. All right. So we have, if you want to know the probability of drawing a king, first thing is that we look at the number of total number of possibilities. So the total number of cards in the deck is 52. And then the total number of kings in the deck is 4. 4 kings in the deck, 1 for each suit. So once you have that, it's 4 over 52, which is 1 over 13. Probability of drawing a king. Any problems with that? Next one, we want to know the probability of drawing a king, queen, or jack. So notice the first statement. We recognize that these events are mutually exclusive, or in other words, disjoint. In other words, they do not have any cards in common. You know, if they had some cards in common, then it'd be a different relationship, different way of calculating. But or we just have to consider something else. But since they do not have anything in common, all we have to do is find the probability of each one of them and then add them together. Everybody done with A? Can I scroll up? So just went ahead and found, even though all three of them are the same, just because there are 4 kings, there are 4 queens, there are 4 jacks, and we're dealing with the same deck of cards. I just went through the process of how you would do them, because there's no guarantee that that will always be the case as far as what you're dealing with in examples in math lab. But if you're dealing with cards, you know, king, queen, jack, this would always be the case. But you may be given some other scenarios. So you would have to find the probability of each one of them individually. So the first thing you do is you establish a sample space, which is 52. How many cards or how many kings there are in the sample space. In this case, it's 4, of course. And then 4 over 52 would be the probability. Same thing, then you do the same thing for queens. 52 cards in the deck, 4 queens in the deck, 4 over 52, then you would do the same thing, same evaluation for jacks. Like I said, because we're dealing with a standard deck of card, we already know it's going to be the same for all 3. But if you were dealing with other scenarios, then you will have to evaluate each one of them individually first to find a probability of each one of them. So now you would add all 3 of those probabilities together. That will be 12 over 52. Reduce the fraction, 3 over 13. All right, any questions, any questions? All right. So the next one, a single die is tossed. Find the probability of rolling a number less than 3 or greater than 3. Have I done with that last one? Okay. So single die is tossed. Find the probability of rolling a number less than 3 or greater than 3. First thing you want to do, as always, is establish your sample space. We know that the number of outcomes in a single die is 6. So that's going to be our bottom number. From there, we're looking at the numbers that are less than 3. That's 1 and 2. And I call L for less than 3. So that probability is 2 over 6, because they have 2 outcomes in that event. Greater than 3, call that G. That would be 4, 5, 6, excuse me. So it's 3 numbers in that sample space. So that's 3 over 6. Now they are mutually exclusive. Notice they don't have any number in common. So that means we can just go ahead and add the probabilities together. And that probability would be 5 over 6. Any problems, any problems? All right, can I scroll up? All right, so for the general addition rule, we're talking about when your events are not mutually exclusive. That means they have something in common. You will add your probabilities together and then subtract what they have in common. And so we'll see why that has to occur in a second. Give you a chance to write it down. All right, let's scroll up. All right, so let's see why that has to occur, why we have to subtract what E and F have in common. So a single die is tossed. You want to find the probability of rolling an even number or a number less than 5. All right. Okay, so first we establish our sample space. We already know when we have a single die, our sample space is 6. The number of our sample space is 6. The first event that we're looking at, rolling an even number. So we're talking about 2, 4, and 6. So that's 3 events or 3 outcomes in that event. And so that'll be 3 over 6 as the probability. Notice I'm not going to reduce it right now. I'll reduce at the end because when we add, subtract them, it would be easier to leave them in this form first, then add and subtract them, and then reduce at the end. So we'll leave them like this. So the next one, number less than 5. So the number less than 5, we're talking about 1, 2, 3, 4. So there's 4 outcomes there. And that should be an L. So the probability of L less than 5 is going to be 4 over 6. All right. Problems with the first 2, even number less than 6. All right. So now we recognize that these 2 events are not mutually exclusive because notice they have 2 and 4 involved in both. So they're not mutually exclusive. They have 2 and 4 in common. So that means we do have this scenario. It is possible for a number to be even and less than 5. So that's 2 and 4, and that probability is 2 over 6. So now that we have all 3 pieces, we can go and plug them into the formula. But the reason why we have to explore this right here and then subtract it is because if we do not, when I add this probability to this probability, notice I will be counting 2 and 4 twice in my addition of probabilities. So when I add them together, I'm actually going to get, 2 and 4 being counted twice. If I were to add those together, 4 over 6 plus 3 over 6 would actually be 7 over 6. But remember, our probabilities cannot go over 100 or go over 1. And so that will present a problem. But the reason why that occurs is because we're counting 2 and 4 twice. So in order to prevent that, that's why you subtract that 2 over 6. So that 2 over 4, well, 2 and 4, not 2 over 4, but 2 and 4 are not counted twice, but only counted once. So 3, 6 plus 4, 6 minus 2, 6 will give us 5, 6. All right, questions, any questions? All right, can we scroll up? All right, so we have a single card that's drawn from the standard 52 card deck. Compute the probability of the events of drawing a king or drawing a diamond. So we want to draw a king or draw a diamond. All right, so first thing you want to ask yourself, are the events mutually exclusive? The answer is no. That means they do have something in common. What they do have in common is the king of diamonds. So there is a king that is a diamond. So they do have a card in common. So this is me breaking down the 3 pieces that we need. Kings, what's the probability of getting a king? You know that a sample space, there's 52 cards in the deck, so that's gonna be 52. There are 4 kings. So 4 over 52 would be the probability of getting a king. Once again, I'm not reducing it right now because I have to add and subtract these numbers. I'm just leaving them as they are with the same denominator. Because remember, when you have a fraction and you want to add and subtract fractions, you need that common denominator. So now diamonds, there are 13 diamonds in the deck. So 13 over 52 would be the probability of getting a diamond. And then there is a king of diamonds in the deck, but there's only one. So 1 over 52 would be the probability of getting a king of diamonds. Excuse me. Any problems with anything that's been written before we close that out? Is everybody okay? All right, so now that we have those 3 pieces, we can go ahead and calculate. Notice we got a probability of getting a king, probability of getting a diamond, and minus the probability of getting a king of diamonds. So we don't count that king of diamonds twice. 4 plus 13 minus 1 will give us 16 over 52. Cancel out the 4 in each, and that'll give us 4 out of 13. All right, any problems? Got one more thing, then we'll be done. All right, can you scroll up? All right, last thing for this section, looking at the complement of an event. So your complement will be all outcomes in the sample space that are not in the event. The way we will notate it is E with that superscript C, and that represents the complement of event E. All right, so the probability of the complement of E can be calculated if you had a probability of your event by subtracting it from 1, or if you have the probability of your complement and you want to find the event, you can subtract that from 1. And bottom line, what this means is that adding both probabilities together, the probability of your event plus the probability of a complement will add up to give you 1. So all three of those are just variations of the same relationship. All right. So according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? Give you a chance to write that down. All right. So if 52% played the lottery, if you want to calculate how many have not played, then you just subtract it from 1. 48%. All right. Questions. Make sure we're okay. All right, so let's see, I think that's it, yep. So next class we'll pick up at 5.3. Now, what I'll do first, next class is open up the floor for questions. Any questions you may have, feel free to bring them to class, next class. At this point, so at this point, test 1 and test 2. We covered the information for test 1 and test 2. And it should be available. If you see anything different, if test 2 is, I'll check to make sure if I posted test 2. I may not have, because I might have been trying to figure out if I was going to do that one in the same fashion. But that's what you are responsible for up to this point. And we got into chapter 5 today. So try the stuff out. If you have any questions or nothing else, take a look at the test reviews. See if you see problems in there that you want me to talk about, and we can go from there. All right. Any questions? Any questions before we close out today? All right. All right. So you guys have a good one. Be safe, and I will see you on Wednesday.
You too. Have a good rest of your afternoon.
Thank
Take
you.
care.
Same. Take care. Thank you.